Hello, guys. My name's Emily, and today I'll be discussing the experiment chromatography. So, before you get started, make sure you have your PPE, all of the reagents and equipment necessary to carry out this reaction, and that you have a can of tomato paste necessary. The three learning objectives for this experiment are to interpret the results of chromatography, to identify the solvent that separates the compounds best, and to calculate RF values for different pigments found in tomato paste. So black ink is actually a mixture of many different colored inks, and you can separate these colors through chromatography. So this is possible because each different color has a different pigment in it, and chromatography takes advantage of intermolecular forces, and intermolecular forces can influence solubility trends, and that's basically what chromatography is. So there are three types of intermolecular forces: hydrogen bonding, dipole-dipole interaction, and London dispersion forces. So the first is hydrogen bonding, and it is the strongest intermolecular force due to the interaction between two polar groups. So this image shows the hydrogen bonding between para-nitrophenol molecules, and so this interaction occurs when a hydrogen atom that is bound to a electronegative atom like oxygen or nitrogen, and it bonds with another electronegative atom on a different molecule. So this interaction can stabilize molecules, and this force is the strongest intermolecular force. So because of that, it's also the hardest to break. The next strongest, so the second interaction is dipole-dipole forces. So these are molecules that have fixed dipoles, so a positive and a negative end on a molecule, and opposites attract, right? So the positive end of a molecule will align with the negative end of another molecule. So this example here shows water. So this one water molecule will interact with two other water molecules. And so this oxygen is the negative part of the water molecule. So it's going to interact with the positive part of another molecule. So the hydrogen of another molecule. So the third and weakest force is van der Waals. Or London dispersion forces. And these are actually seen in every single molecule, but they're primarily seen in nonpolar molecules because nonpolar molecules don't have any other intermolecular forces. So since these are the weakest, they're also the easiest to break. So this lab is specifically dealing with hydrocarbons, and some hydrocarbons have more than one double bond. And so conjugated double bonds can alternate with single bonds in hydrocarbons. So you can see here that this molecule is conjugated, but this molecule is not. So this molecule alternates between double bond, double bond, where this molecule is double bond, single bond, double bond. So this one is not conjugated, and this one is a conjugated diene. Carotenoids are hydrocarbons that have a large number of double bonds in them, and carotenoids are the reason that tomato paste has such a deep red color. So the three compounds that you're going to be working with this week are vitamin A, lycopene, and beta carotene. So if you look at all three of these structures, you see that there's alternating single bonds and double bonds. So these molecules all have conjugation. And so conjugation is the overlap of the pi bonding orbitals. So the double bonds have pi bonding orbitals, and the longer the conjugation system, so the longer the alternation of single bonds and double bonds, the closer those orbitals become to overlap. So the easier it is for an electron to jump from one to the other. So also because they have such a, like these three carotenoids have such large conjugated pi systems, they absorb light in the blue part of the spectrum, so high energy, short wavelength. Therefore, they reflect and appear red color, hence giving tomato paste its deep red color. So we said the longer the conjugated system, the closer the orbitals are, right? So the closer the orbitals, the electronic transition will occur at lower energies. And the lower the energy, the redder the wavelength. So go back to that slide before and think about which one of those molecules has the largest conjugation system, and that will be the reddest carotenoid. And so remember that those conjugated double bonds is what gives carotenoids their color. So a very important aspect of intermolecular forces is solubility trends. So a really large takeaway from this experiment is the rule likes dissolves like. So polar solvents dissolve polar molecules and nonpolar solvents dissolve nonpolar molecules. So this is possible because the solvent and the solute have similar polarity, hence similar intermolecular forces. So since the carotenoids are long hydrocarbon chains, they're nonpolar, right? So they should dissolve in nonpolar solvents. And in biological systems, fats and membranes are nonpolar environments. So intermolecular forces are also a big determining factor of melting and boiling points. So since hydrogen bonding is the strongest intermolecular force, it also takes a lot more energy to break that type of intermolecular forces. So compounds with hydrogen bonding typically have a higher melting point than compounds strictly with London dispersion forces, because London dispersion forces are much easier to break. So chromatography separates compounds based on polarity. So the chromatography paper is polar, so it will interact with polar compounds, right? Capillary action pulls the solution up the paper, so think about how compounds are going to separate. Are polar molecules going to be towards the bottom, or are they going to be towards the top? So after you watch this video and you're still struggling with the concept of chromatography, you should go over this example on the top. It's actually like a pretty relatable example, and it can probably help you think through it. So a couple things to remember about chromatography. So it's used to separate and or identify compounds, because all compounds have different polarity, right? So they're going to move up the paper at a different speed per se because of their different polarity. They're going to interact with the polar paper differently. The second thing is that the paper is considered the stationary phase. And the third thing is that the solution is your mobile phase. And so from here on out, we're going to be talking about mobile phase and a stationary phase. So remember those two things. Chromatography is analyzed by what's called retention factor, or RF. So this is how far the spot travels over how far the solvent travels. And so this value is very useful if you're talking about a specific compound used in different solutions, or you're comparing two different compounds in the same solution. You can just, in your discussion, you can talk about comparing those different RF values. And so you will take the spot distance divided by the solvent distance. And so RF is always a decimal and will never have units, because you're dividing units over units, right? They cancel. So it's just a decimal. It's just an arbitrary number to compare different compounds. And so this picture is almost exactly what your chromatography paper should look like. So in the middle, you should have your tomato paste that will have all of the different carotenoids, right? And then on one side and on the other side, you're going to have your standard carotenoids that come in your kit. So this is how your paper should set up. I recommend that you label your plate or your paper so you know what lane is which. And then to calculate your RF value, you're just going to take a ruler and you're going to get the distance of this spot, and you're going to divide it by the distance of the solvent. So to spot these on your paper, you're going to use the capillary tubes, and you're just going to take up a little bit of solvent, and then you're just going to spot it once on this tick mark. The mobile phase for this experiment is going to be a ratio of petroleum ether and acetone. Remember to let the petroleum ether and acetone does just evaporate on your windowsill. Do not, do not, do not, do not put them down your sink. The key to chromatography is to achieve the best separation between the spots. You do not want your paper to look like this. It should look like the 3 lanes. And so how do you achieve the best separation? So you can actually change the mobile phase. So you can change it from petroleum ether to acetone, or you can do a ratio of the two. And that, like, using a ratio and varying that ratio will change the polarity of your mobile phase, meaning that your compounds will move up or not move, move faster or move slower up the plate. So it's this part of chromatography is really all about trial and error, what works best. My top 3 takeaways that you should understand from this experiment is that likes dissolves like. Remember that rule. RF is always a decimal and is unitless. Don't put units on your RF. And the third thing is that more polar compounds stick to the bottom because like dissolves like, they have higher interaction, the polar plate. Before you start the experiment, remember your tomato paste, remember your PPE, and if you have any questions, you guys can tune into our office hours. Thank you.